very much for giving me the chance. So I'm going to be talking about fractals, but before we get there, I'm going to be starting up with a really simple small question, which is, what is there? Okay? I'm going to be showing you a series of pictures, and I would like you to look at them with sort of an analytical eye, to see what I might mean when I say that. Okay? Here's a good Finnish swamp with some birch trees, another greenery. There's a good Finnish hilltop. It's not supposed to be a tourism advertisement for Finland, but anyhow. Then there's some water splashing, and then I have a picture taken from an airplane. I don't know exactly where. And now these are all natural objects, okay? And I've chosen them for a reason. What do you see in them? Then there's a good Finnish thunderstorm. Moving on to Scotland, good Scottish clouds. What else do we have? We have good Scottish hilltops with yours sincerely, who doesn't really fit the picture of analyzing and describing what's going on, but it was the best I had. Then there's some pine tree branches, and now maybe by now you already see what I'm trying to sort of make you see, which is that these natural objects, they seem to have a lot of intricate detail, and I don't know, they seem to be sort of tangles of detail. Okay? And then somehow they seem to be repeating themselves. As you can see in this tree picture, for example, you have a bigger branch, and then smaller branches branch off of it, and then that keeps on continuing. You have smaller and smaller branches. The same with the hilltops. I don't know if you noticed, but there was a hilltop, and then on the hilltop you could see stones of the same form as the hilltop itself. And you can see this in the nature. It's very small scale here in frost crystals, inside us, in lungs, for example, here, or in way bigger scale in the shape of the coastline here, coastline of Britain. And somehow, when you think about it, why would these patterns appear? For example, in the case of the tree branches, what the tree wants to do, it wants to catch as much light as possible without pushing its branches too far away. So it's sort of trying to fill up the space with lots of leaves to catch the light. The same is true about lungs. So we're trying to feed them inside a person, but we want them to have a very high capacity of changing gases. So we want them to have a huge area, and we want to pack them there. So, so then the next question that I want to ask, so this is what we see, and the next question that I want to ask is why? Why do we see this kind of elements? Why do we see these kind of patterns? So now, if I was a tree, I wouldn't have a lot of time to get it wrong. I would need to pack the space, and I would need to get it right soon, because otherwise somebody else is going to catch that light. And if I was to create that kind of space-filling creature, then what I would try to do is I would try to give it some sort of law of, I don't know, creating branches densely enough, and then just repeating that over and over and over, all over the place. It's the same with the lungs and the frost crystals. Is that what makes it look so intricate and detailed is just this kind of simple branching law that is given to it by some sort of force or genes or some sort of power, and then it just keeps on repeating that law. And once we give it long enough time, then we start seeing these horribly, incomprehensibly detailed images. And it's quite effective, and it creates this huge complexity in relatively short amount of information given in the beginning conditions. Okay. But then, if we want to understand this kind of objects, as we want to do as scientists and as physicists want to do, and mathematicians to some extent, we want to understand these kind of objects. They have so much of detail and so much of, how do I say, irregularity or roughness that it becomes almost impossible to describe them using classical geometrical methods. And there is the simple example of that, which is the coastline paradox, which was first discovered by a guy whose name I will check from this paper, Louis Fry Richardson, who tried to measure how long is the coast of Britain. He noticed that if you start measuring it using a ruler of specific length, then you get one answer. So the picture on the left hand side, you have some sort of relatively long ruler that you're using to measure the length, and then you get this curve, and then the length of the curve is one estimate of the length of the coastline. But then when you change the ruler to a shorter one, and then yet to a shorter one, you seem to be getting longer and longer and longer answers, longer and longer coastlines in Britain. So it looks like the coastline, the length of the coastline is not well defined. And this kind of simple geometrical approach doesn't give you anything that you can use. So this is a failure of classical geometry in describing these kind of natural objects, which seems a bit scary, because we would like to be able to use simple mathematics to describe these objects. But then we have infinite curiosity of researchers, and then they come up with mathematical objects that will somehow better fit this kind of objects that we see in the nature. I'm sort of going to be talking about iterated function systems, but let me first begin by explaining to you what kind of mathematical objects they could be. So here you have a very simple example of a set that will somehow exhibit the same behavior as those coastlines and frost crystals and hilltops and whatnot. This is the four-corner counter set or counter dust. And what I do in this picture is that I have this left-hand square, and I pick the four corners of that square, and then I keep on picking the four corners inside those squares, and then I keep on picking the four corners inside those squares. So in the first level I have 4 squares, in the second level I have 16, and then I just keep on picking the squares inside the squares. And what happened when I was drawing this picture, I was zooming into this picture to make sure about some detail. Not that I still got it right, you can see that they're a bit wonky. And what happened was that for a moment I wasn't quite sure at which scale I am. I didn't know if I'm in the second or the first or which iteration I'm looking at. And that's exactly the kind of self-similarity or self-repetition that I want these sets to have. So when you zoom in, you see exactly what you saw in the largest scale, and then you don't know where you are anymore. And that's exactly what happens also when you zoom into a picture of a tree branching. When you're looking at the tiniest branch, it keeps on branching and you cannot tell whether it came from the huge tree or whether it's just a sprout itself. You don't know. Okay. I have a bunch of other examples. I'm going to run you through some famous fractals. Here's this Sierpinski gasket, and the iteration law that I had, well, that the person had when they were drawing this, is to start with a triangle and then pick again the 3 corners of the triangle like this, and then you just keep on iterating this inside itself, and then in the limit that's what you see. So you can think that I have this kind of simple law, I start iterating it, and then I end up having something immensely detailed. There's a Sierpinski carpet, which is a cube with divided into 9 pieces, of which I either pick the 8 outside ones or the middle one, depending on which picture you want to. If you want to think about the black boxes as the set or the white boxes. Then going into higher dimensions, there's no reason why you would have to only look at plane subsets. You can also look at the original object, and you can see that so this is the Menger sponge, and it's actually from the same iteration law, but I just have a 3D cube which I've divided into 9 times 3, 27 pieces, of which I picked the outermost ones, making a hole in the middle. And then, for a bit different purpose, if you think about the lungs or the tree branches, here is a Peano curve, which has so here the iteration law is visible, so you start with the top left corner, and then you continue as if you were reading your book. And you end up having a thing that becomes more and more, that this is a bigger and bigger portion of the, not really stays one dimension, but that visits more and more of the square that you started with. This is an example of the space-filling curve. So if you imagine continuing until infinity, or if you imagine continuing this process infinitely long, then you will end up having something that is space-filling. And that's somehow something that the norm also looks like. And it's also obtained from the simple iteration law. And then here is from Koch snowflake, which is coming from a law that looks like this. So you start with the lines element, and then you replace it with this. Okay, so this is just to give you some heuristics on what kind of sets I mean when I talk about fractal sets, and what do I mean when I say that they somehow exhibit the same behavior as the natural object that we saw in the beginning. To hit you with some hard mathematics, I'm going to tell you now what is an iterated function system. And to make it less scary, all of these sets that I just now showed you, all these pretty pictures that I just showed you, they are obtained from these iterated function systems. And now, I first define a mapping to be a contraction if it decreases distances between points. So I begin with 2 points x and y, I map them with this mapping f, and after applying the map, the points seem to be close together. Okay? And then I call this contraction the amount that is, so I don't know, here is the distance in the beginning. I don't know what to call it. Let's call it. Here's the distance in the beginning, and then the distance in the end is smaller than r times the distance in the beginning. And then this is called the concentration of the map. And now if I have a collection of such contractions, and then I iterate them, then I obtain a map. I obtain a set F, which is invariant under the collection of maps. What do I mean by that is that, for example, if you think about the shear PC gap that I showed you in the beginning, the 3 maps that define this set are the map that takes this whole triangle into this triangle, and the second map is the one that takes the whole triangle into this triangle, and then the third map is the one that takes the whole triangle into this triangle. Okay? And if you imagine the whole structure being mapped by these 3 mappings, you would just obtain the 3 pieces of the same picture from these images. Okay? That's what I mean when I say that this set F, so this shear basic triangle, for example, would be a set F which is invariant under an iterated function system. And I can also obtain it using this kind of iteration law. that I described when I was showing you the sets. So I can also describe it saying that this set F, I can also describe saying that let me take these 3 corners of the triangle and let me take these 9 corners of those 3 triangles and so on. Okay? And now, usually sets that are defined through these IFSs, they do have this coastline, they do somehow exhibit this coastline paradox, which was that they were not easily described by terms of classical geometry. Okay, I'm going to give you a very simple example that we are going to be stuck with for a little while. So all of these fractals that I showed the pictures of are in a way more fancy, or they have a bit more flair than this one, but it is a good solid example, and it's difficult enough to actually produce most of the properties that we are gonna need, and even later on in research is a good example to have in mind. So I'm gonna start with the unit line segment, and then I'm gonna divide it into 3 pieces, and then I'm gonna drop the middle piece. Okay. So I have 2 line segments left. And now, following this iteration process that I want to use when I'm defining fractals, I just keep on dividing these intervals into 3 pieces and removing the middle piece. Okay? And now you can imagine, much better than I can draw, what the end result would look like, perhaps. So if you keep on doing this forever, you end up having some sort of dust of points. Doesn't really make sense to draw this in a computer because it's just kind of a small example. But now this set also this set is also hard to describe using classical geometrical methods. Now, why is that? As I said, it's a collection of it's a point dust. So it consists of these discrete points, okay? And how many points do I have here? I have here exactly as many points as I have. Let me look at the construction again. So if I take a walk down into construction, I can take a step either to the left. I can take a left construction interval, or I can take a right construction interval, right? And if I take an infinite walk down the construction, I always end up in a point of the set. There's going to be something in there because it's a nested sequence of closed intervals, and that point is going to be a point on the set. So if somewhere here I have the one-third Cantor set, and all of these walks that I can take lead up to a point in the Cantor set. So now, how many points I have in this set is exactly the same question as asking, how many walks can I take down this construction? And the answer to that is infinitely many. Even uncountably many, if you have ever seen the diagonal argument. And then another reason, which means that I cannot measure this set by asking how many points does it have. It doesn't give me a reasonable answer. Okay? Well, then the next measure that I have is the length measure, right? That's the next step up. I'm dealing with the sets on the line, so maybe it does have positive length, and that's why I end up having infinitely many points. Okay? Well, it has 0 length. Like a cheaty way of seeing that would be just to say that if there was a positive length there, then I would just divide that positive length into 3 pieces and remove the middle part, so I wouldn't have that positive length anymore, I would have something smaller. You can also see it by summing up the lengths of the removed intervals, and that would be the non-cheaty way. Now, if you're finding this somehow difficult to grasp in 2 minutes that I used to explain it, no wonder. The first guy who defined this, Georg Cantor, he went crazy thinking about this set. He died in an accident, I think. But yeah, so this is just to describe to you that even in this simple case, the coastline paradox takes place, and we cannot describe this set using. So this is a fractal set, and we cannot describe it using the ordinary classical geometric method. Something else needs to be done. We need to have something else to describe how big it is. Okay. Now, what is that something else? We are not so okay. Let me emphasize one more. So this set is not just a collection of infinite collection of points, right? Because I don't know, if you take all the integer points in the real line, it doesn't look anything like this set. This set has somehow more structure. So it's not just an infinite collection of points, but it's also not just a point, because it has so many of them, right? So that's why. Okay, I hope you believe me now that we need something more to describe it, and that something more is measure dimension. That's what I'm going to be describing in a second. Okay, so why do we expect the coastline measurement to give us the length of the coast of Britain? We expect that because if you have some sort of classical nice curve and you start approximating its length using this kind of line segments, and then you take shorter and shorter line segments, you get closer and closer to the actual length. So if you have a curve like that, the black curve there, and then you start approximating using the blue curve, which could be a bit brighter and thicker for people to see better. But anyway, you get some estimate for the length, and then you take the red curve and you get a bit closer to the actual length. And if you continue this process, in the end you're going to get the actual length because it has a well-defined length. But as we saw in the case of the code in Britain, this doesn't happen in a fractal set. So you start approximating and something goes wrong. You don't get a sensible answer because it doesn't have a well-defined length. And what exactly goes wrong is that you have these line segments and you are summing them up together to get an estimate for the length of the curve, but you have too many of them. So you have the number of line segments that you need to cover to your set or to approximate your set growing much faster than the length of the line segments goes to 0. Okay? And now how do we catch what this much faster is? Let's look at simple examples some more. So here I have a very simple example of the line segment. People can see. I have a very simple example of a line segment of unit length. I know that it has unit length, so I can trust myself that I'm going to get a good approximation when I start approximating using smaller and smaller line segments. So let me take a line segment of length r, and let me give an estimate for the length of this line segment by covering it with these smaller line segments of length r. Now I'm asking, how many do I need? Well, I'm going to be needing about 1 over r of them, okay? There might be some constant coming up, but the constant is going to be, well, it's going to be a constant. It's going to be of size 1, roughly. And the 1 over r is, well, is a very, very small number. So it shouldn't be a problem. Another example, if I consider a cube, which also has a very well-defined two-dimensional volume or area, because it's a two-dimensional set and it has a well-defined two-dimensional size, which is 1. And I want to estimate the size of this set using the same idea, that I just want to cover it as well as I can using those smaller cubes, which have side length r, and I want to understand, well, I want to get an estimate of the size of the bigger cube using that. Okay, what happens? It looks like I get about 9 of them in this picture, but in general, in both directions, I get about 1 over r of them. Right? Which means that all in all, I'm going to be getting a covering number, which I denote by nr, of 1 over r squared. That's what I see. And I don't have to worry about the cubes being a bit wonky again. I'm going to say about the pictures that I have been stealing lots of work from Wikimedia Commons, but I try to attribute it to the people who have done the work. And then there are some pictures of my own, and also the wonky ones, as you can something. Okay, so this was a two-dimensional set. We get 1 over r squared. When we had a one-dimensional set, we got 1 over r. If we had a three-dimensional set, say a cube, like a proper cube, three-dimensional cube, and we started to cover it using smaller cubes of side length r, we would get 1 over r in every direction, which means 1 over r cubed, right? So it looks like when we have a one-dimensional object, we get a power 1 here. When we have a two-dimensional object, we get a power 2. When we have a three-dimensional object, we get a power 3. Okay? It looks like this power in the covered number is telling us the dimension of the set. And that's exactly what is going to be the first dimension, notion of dimension that I will introduce. So I'll need the counter set in a second. So let me erase this. Okay. So what do I need to do? I have some weird set, and I have let's use cubes because we were using cubes before. I have a covering set which is a cube of side length r, and I want to cover this set as optimally as possible using those cubes. And I ask, how many sets did I need? And that's my nr, the covering number. So I need to find an optimal cover, and then I just need to count how many sets did I need for this optimal cover. And then I need to somehow extract this exponent from that information, and that's just done by a little bit of magic. So I just take logarithms, and then to make sure that this was not just a gimmick of this particular scale that I happen to pick. For example, if you take big enough r, you can always cover your set with a huge cube. So to make sure that this is not just some sort of irregularity in the behavior, I let r go to 0 and look at the limit. And that's going to be my first notion of dimension. And this is a proper notion of dimension which is used in the study of fractals. It's called the box dimension. It has also some very good practical properties because there's a variant of this definition that is really easy to use in practical situations when you are looking at these actual natural objects such as coastlines and trees. Okay. Now let's do this calculation for the counter set. Okay. I'm not gonna cover it using R balls because there is a cheat. There is a theorem that says that I can only cover it using exponentially decreasing scales. Okay, so I'm gonna be covering it using sets of size 1 over 3, 1/3 to the power k. So on the first level, I'm going to be covering with on the first level. This is the first level of construction. This is the second level of construction, and so on. And now all of these, and this is the case level of construction, and all of these construction intervals that I have drawn, they are going to be at all levels. They are going to be giving me a cover of the set. Because what was the process? I was just removing pieces from them. So if I'm removing pieces from them, then all of these collections at whatever scale are going to be giving me a cover. So I'm going to be covering with here 1 over 3 to the power 1, 1 over 3 to the power 2, and so on. And here 1 over 3 to the power k. Okay? So what's the covering number? Here I need how many? 1, 2. So here my nr, well, n 1 over 3 to the k, here's my 1 over 3 to the k, is going to be 2. Here it's going to be 2 squared, and maybe a little bit of induction gives me 2 to the k at the case level. Every time I divide into 2 pieces. That's where the 2 to the k comes from. Okay? What does it mean? So I have nr, what was log of the covering number over minus log of the size, right? Well, covering number was 2 to the k. And the size is just, well, minus log of 1/3 to the k. And the k's come out and cancel. The minus cancels the 1/3. So I end up having log 2 over log 3 as the dimension. Okay?
Sorry, what is this dimension again now?
The dimension is the exponent that the covering number takes when you go to smaller and smaller scales. Which in the case of a one-dimensional set, a line segment, you got 1 over r to the power 1, right? And then in the two-dimensional case, you got 1 over r squared, so the 2 was the power. So now your r is 1/3 to the k. So how fast does this number grow compared to this 1/3 to the k? When you look at how fast this number grows, you get 2 to the k, and then you have this 1/3 to the k somehow counteracting, because that's going to 0 fast as well. So when you extract the exponent of the covering number, you get exactly this. So this is what you would put down there. This is what you would put down there into the power of s, into the power of r, sorry. So here you would have log 2 over log 3 in the first calculations. Okay? And then there's of course an argument to show that this is an optimal cover, but let's not get to that right now. Okay. So this is already some notion that describes how complicated our set is. This d, this dimension number. But if we want to, so what the original problem was, we wanted to understand how long was the coast of Britain, right? And we noticed that the problem was that we cannot approximate it using one-dimensional sets, because the number of one-dimensional sets that we need to cover grows too fast compared to the size of the covering sets. And then the question was, how fast, how much too fast does it grow? And the answer was that we need to extract this exponent. So this is how much too fast does it grow? How much too fast does the number of covering sets grow as compared to the speed of the covering sets going to 0? Okay? Okay. Well, that was not what we wanted to know. We wanted to know how long it is, right? And so we need some notion of, so now we know what goes wrong and how badly. This is how badly things go wrong. But we want to also know how long what is the number, what is the measurement that we get. And now this looks maybe a bit scary. So what do we need to do? So now we know how badly things go wrong. We know that they go badly wrong. Okay? So now we need to know some sort of notion of, a d-dimensional measure, right? So for a one-dimensional set, the notion of measure is length. For a two-dimensional set, the notion of measure is area, right? So for a d-dimensional set, where d is not an integer, then how do we measure the size? We need some notion of d-dimensional measure, and that's the notion of d-dimensional measure. The pieces there are kind of familiar, I hope. There's the covering, there's the small size of the covering sets, and then here's what we do to somehow counter the way that things go wrong. That's in this power d. But maybe just, let's not live with this for too long. Let me just mention that this measure, this d-dimensional measure, behaves in exactly the same way as we noticed what happened here with the counter set. So we noticed that just counting the number of points is not good enough because it gives it an infinite value. And you notice that just counting the length is not good enough, because that gives us a value 0, right? So, and the problem was that this set is log 2 over log 3 dimensional, so both of those measures are wrong. And that's exactly what happens in general, so that we have this d-dimensional measure, and it stays infinite as long as it reaches the dimension of the set, and then it drops to 0. And this place where it drops, the place where we have some hope of getting a number that is positive and finite for the measurement, for the length of the set, or for the d measure of the set, that's what we call the dimension of the set. And this gives another notion of dimension. Now, this box dimension that I described before, and Hausdorff dimension, they often agree, but not absolutely all the time. Okay, take-home message. What do? We give the covering sets this kind of an edge. We give it this kind of a tool to fight against the covering number growing too fast. And that's what happens here. That's where the D comes from. Okay, to end up this measured conversation with something concrete, the Hausdorff D measure of this set, of this one-third counter set, where the D is this dimension log 2 over log 3, is exactly 1. That's a nice positive and finite number. Numbers don't get much better than that, actually. Okay. So let me quickly list some problems in fractal geometry that people study, as in researchers in fractal geometry, what kind of questions we are interested in. So first of all, there's the question of finding the dimension, and many problems are this form. So if you have a certain collection of maps, of these contracting maps, and then you want to understand what is the dimension of the corresponding set. For example, I'm just going to flash it at you. If all of the maps are similitudes, which means that they contract all distances by the same amount, and there is a certain separation condition that holds, then the dimension, both of the dimensions that I described, are given by a number that satisfies this kind of formula. In fact, all of the sets that I showed to you earlier are sets that satisfy both of these conditions, which means that all of their dimensions are given by this formula, where these Ri's are the contraction ratios of the maps. And if you plug in, let me just quickly, if you plug in the counter sets, so you have two maps, both of them contract distances, so they take this length 1 interval into two length 1/3 intervals. So both of them have contraction ratio 1/3. So the formula becomes 1/3 to the D plus 1/3 to the D. This is the first map, this is the second. This comes from the first iteration law. And you want to solve this. You want to solve for the D, which gives you 1. And that's exactly that value. So the solution to this equation is log 2 over log 3. Okay. Other problems. Well, first of all, I should mention that fractal. Okay, what do I mean by fractal geometry? Fractals don't have a mathematical definition. There is no way of telling whether a set is fractal or not. But it doesn't stop us. What we do is we study general sets. Often the information that is given to us is, say, the dimension of the set, in which case we need to know that it has that dimension, which means that it's already somehow fractal-like. And then here's a list of things that one can study. So if you are given this kind of general set, and then you want to understand what the slices of it look like, what do I mean by a slice? I mean that you take, say, a plane, and then you in a free space, and then you integrate your fractal with this plane. Or you want to understand what happens when you project the fractal set, or what kind of set can contain a line in every direction. or things like that. Then there's another kinds of problems. What kind of measures can it carry? How do I even go about defining fractals? And so on. Okay. So that was the hard mathematical part of what I wanted to say. Let me finish off by a bit different kind of material. So first of all, going back to the coast of Britain. The coast of Britain, the dimension of the coast of Britain has been calculated using this method, this box counting method. And the value that they got, it was Benoit B. Mandelbrot who studied this problem, and the value that he got was, let me check, 1.25. Okay? This explains why the length measurement went wrong, because length is a one-dimensional measure and the dimension is higher. So this is the dimension of the coast of Britain. I don't know if anybody's checked the measure in that dimension. Probably they couldn't. Now, I wanted to tell you about how to use fractals in practice, but there is a problem, because I was describing here, I was telling you that you need to make sure that somehow this covering behavior, this covering number growing too fast behavior, happens at all scales. So there has to be some sort of power law telling you how big the covering number is going to be compared to the size of the covering sets. Now, if you go about the real world, you are not going to be able to be covering with sets of size 0, or even very close to 0, because there's, I don't know, particle size, which gives you a lower bound. So in real world, there are no real fractals, because in real world you cannot take limits. There is no infinity in real world. And there's another problem, which is that, so what do I mean when I then say that the dimension of the coast of Britain is 1.25? I just mean that it obeys this power law up to some scale. And amazingly enough, it seems to behave the same way, at least on many scales. And that's already surprising enough. But the problem here is that it's very hard to understand why. So if you want to do, I don't know much about experimental sciences, but if you want to claim that something is a good model for something in the real world, you need to be able to cover, first of all, you need to make an observation that it looks like that. That's the starting point. So that's what we have obtained. We know that it looks like it has dimension 1.25. But then, from this number, or from this observation, we need to be able to build a theory, and then use that theory to somehow predict what happens. And it's very hard to build those theories, because the forces that shape natural objects are so complicated. So I can wishy-washy just explain to you that, oh well, there's like waves coming from this direction, and then there's wind, and then the stone is harder in some places, and that's what creates the shapes of the coast. But that's not really an explanation, that's not really any sort of scientific theory. So it's very hard. You can observe this kind of power laws, for example this, and then clouds for some reason have the boundaries of clouds have a dimension 1.36, for example. But what does the number mean, and where does it come from? Nobody's very well able to explain. And the problem is that the forces that shape nature are so complicated. There are so many laws affecting. For example, the simple tree branching is not well understood, which was a surprise to me. Just for the purposes of this talk, I was trying to find out when does a tree branch? Turns out that there's a complicated, some sort of enzyme reaction that creates a branch, but one cannot predict exactly where it happens. There's also the genes of the tree affecting, and where does the sun shine from, and all those things. There is some factor that we can take into account using mathematical methods, and that's the randomness of the process. So that's not really a problem. Statistical laws are well within our reach. Okay, so what has been established then? What kind of connection have actually, so not just observation, but what kind of connections have really been established? There is Brownian motion, which is a model for describing how does a pollen particle move on a surface of water. So you have pollen floating in water, and then you want to understand how it moves. And this can be well described using Brownian motion, which is a statistical fractal-like model. And all these three corners of observation, theory, and prediction have been covered for this particular problem. And then I was once in a conference, and then I was giving a talk on fractals, and then a guy came to tell me that they are using this to study. They are trying to use fractals to diagnose cancer. And to be honest, being a pure mathematician, I wasn't that keen on hearing it, but he started me. And then, again, just for the purposes of this talk, I went and Googled, and there is some research going on about this. And if you think about it, it makes sense. So an ill cell, a cancer cell, will have a different growth factor, will have a more aggressive growth factor than a healthy cell, which means that this kind of power law, this kind of covering set amount law, is going to behave differently for a cancer cell than a healthy cell. So I don't think it's actually surprising. I don't know, but yeah, but they're actually using this kind of dimension estimation methods in diagnostics. I don't know how widely. Then they have been using fractals. They have made this observation that stock market behaves in a statistically self-similar way, but that doesn't really. I mean, that's not going to make me rich. I was once talking to a guy in Hong Kong who said that he's going to become rich by using fractal methods in finances. I don't think he got rich, at least not by yet. The problem is that stock market is so highly random that any sort of model is going to be poor at predicting what happens. I saw this very convincing pair of pictures where they had a stock market. Some sort of, this was a real observed behavior, and then they had modeled the same behavior, but they had removed the, I don't know, so and so many biggest discontinuities in this graph. And so I'm actually drawing it wrong. It has these huge jumps that are very hard to predict. And somehow, all in all, the shape was the same, but the end result was very, very different. So you can sort of locally see what it's going to look like, but you cannot predict it over a long time. And fractal geometry doesn't really give you any sort of very strong tools to overcome this problem. But on a positive side, so it turns out that if you know the dimension of a natural object, and then you tell a computer to draw a fractal of that dimension, you are actually going to see an object that looks very much like a natural object. So if you tell a computer to draw an object that has dimension 1.36, then it looks like a cloud. And they are using this. They are actually using this drawing computer when they're doing computer graphics, when they are making games and stuff. There's a couple of examples. This is the Barnsley fern. This is just a deterministic fractal, and then here are some fractal weaves. So you can see that creating natural objects is relatively easy using these kind of iterative laws. And funnily enough, I came across a fractal camouflage pattern company. They say that it's much more natural than this kind of pattern that you can create using some sort of hand description. So, okay. What else did I mean to say? Oh yes, and there's a very important part. I'm sorry, I'm going to be ending by 9. We
started a bit late, so you can go on 5 minutes plus.
Yeah. So there's another thing that I wanted to say, which is fractals in art. If you Google for fractal art, you're going to get your whole browser full of pictures of all kinds of things. People use computers to create these kind of iterative processes and then draw them. But this is a very old one. This is some sort of ancient Japanese artist who has drawn a wave. This is kind of a cheaty example because he was drawing a wave and he had observed that it looks like that it has this kind of self-repeating pattern, and then that's what he drew. So it's not that the fractal itself was so appealing to him, but he was trying to catch in the best possible way what the wave looks like, and that's why he draw this kind of self-repeating pattern. But then I have another example, which I'm soon going to give, but it requires me to go off the, sorry. I hope I still have it open somewhere. So there's this guy, Harlan Brothers, who was friendly enough to give me permission to use his work in this talk. I think I like this one best. Where did it go? Please don't do that. Maybe I don't know if you can get a better version of it. Maybe you can go down here and see Harlan Brothers, you can see for yourself. But maybe you could get a feeling for it. Like it's kind of baroque-like music, among other things that he has made. And this behaves in a fractal-like manner. So it has this kind of scaling, or this kind of power. It behaves in sort of power law way. So he has written down the distribution of kinds of the tool and such things. There are many examples in this web page. And the reason so it's not only these visual images that can have fractal-like behavior, but also you can hear them. And what is funny about it is that they are so appealing to us. And again, I began with these fractal-like natural images, and then I asked why. I'm going to ask you why again. And I'm going to leave you with a picture, which is a neuron, a brain cell. And I'm not going to say anything more about that. So let me finish off by saying that fractals are fascinating, I would say, of course, because I'm actually doing research on them. But I think there's something very appealing in them also for somebody who is not interested in all these covering numbers and logarithms and limits and all that. Apparently, they are something that is easy to explain to even very young children. I was told that if you have to go babysitting, for example, you can just show them how to draw the Sierpinski gasket and tell them to go on forever. And it becomes more and more detailed and more interesting the further you go. But then at the same time, they are so complicated that the first guy to ever study them went crazy. I'm exaggerating, he also has some other problems on his life, but still. So there's some sort of interplay between beauty and simplicity, and something very natural for us, and then at the same time something very intricate and complicated. So I now thank you for your interest and for walking all the way down here to the other end of the building to hear this. Thank you.
Anybody have any questions you'd like to ask Henna now that we've finished that fascinating talk? Anybody got any questions?
Can I just ask you about the dimensionality and ask you if I've got the terms right? So, if I was trying to measure a square in 2 dimensions and I was a line, it would appear to be infinitely big. I couldn't measure it.
Exactly.
And if I was trying to measure it as a cube, it would be 0. It wouldn't be anything. But if I get to the right dimensionality, it has an area. So I just need to move myself along to be 1.25 dimensional, and then I can measure it.
You are spot on.
Okay,
yeah,
great.
Extremely good. Thank you. Yeah, good. Yeah?
Has anyone found out how long you can keep on drawing the lines?
You can keep on, well, you can imagine keep on drawing on forever. But in practice, there is limitations because, I don't know, no matter how big you start, your pen is not sharp enough to go on forever. So it's only in our imagination where you can go on forever.
We cheated this morning when we were doing it. We kept pretending to zoom in, didn't we?
Yeah.
And then we were drawing it again and pretending to zoom in again.
Oh, I see.
So we cheated
Okay, well, thank you very much again, Henna. We're going to be moving to the SCR now for free wine reception. Everyone's welcome to join us. Thank you very much.